Hello, this video is for Stat 210, Handout 6, and it's going to cover pages 7 through 13. Okay, let's go ahead and get started then. So the example that we were looking at had to do with crime rates in a particular neighborhood around the University of Minnesota, and we were wondering whether or not there were differences in the crime patterns throughout the year. The observed data that we had here was 32 in the fall, 17 in the winter, 30 in the spring, and 24 in the summer. We were setting up the null distribution under what it would look like if the crimes were equally likely to occur. So if they're equally likely to occur, there was 103 total. There should be around 25 or 26 as our expected outcome for each season. We left off in class talking about the fact that 32 was not really an outlier, 17 was kind of on the edge of being an outlier, and then 30 for the spring was not an outlier, and 24 was not an outlier. So what we had in class is something like this. Fall was not, winter was maybe a yes, so that could be a maybe, or maybe it was a yes there, and then no. And we had to make a decision about whether or not crime patterns were equal throughout all 4 seasons. And we talked about in class that the fact that 3 of them were at no and 1 of them was at yes makes it difficult to try to make an overall decision. So if you went with the majority rules here, you would say no, because 3 of the 4 seasons were not outliers. The other thing that we could do to make this more formal is compute p-values for each of these. So the p-value, again, the definition of a p-value is just values the probability of observing an outcome as extreme or more extreme. So if we do that for fall, more extreme is going to be values off to the right here. So there'll be 1, 2, 3, 4, 5, 6, 7 on the high side. But we could have differences if we were too low against the expected as well. So these are going to be two-tailed probabilities. So we had 7 on the high side. 32 is, 6 away from 26. So the mirror image of 32 would be at 20. So on the low side, we would be counting 1, 2, 3, 4, 5, 6, 7 dots down here as well. So if we were to compute the p-value for fall, we would have, 7 dots on the upper side, 7 dots on the lower side. That's going to leave us with 14 total. The p-value is going to be, there's 100 dots on those graphs, so the p-value would be 0.14 if we were to do it in this way. If we were to compute the p-value for winter, winter was at 17, so there's 3 dots down here. 17 is 9 away from 26. So we got to go 9 up, which is going to be 35, and there's not any on that high side. So we have 3 on the low side, 0 on the high side for winter. So high side is 0, 3 on the low side. That gives us a total of 3. 3 divided by 100, again, is going to be 0.03. So technically, that 17 is an outlier in that distribution for winter. The other 2 are not going to be extreme. I'm not going to count all the dots here, but we got a lot of dots here for 30 in the spring. So greater than or equal to 30, and then that's 4 away, so we'd have to go less than or equal to 22 on the other side. That p-value is going to be way bigger than 0.05, and the same thing for summer. So I'm not going to calculate those, but they're going to be much larger than that 0.05. So what we're going to end up with is, again, a situation where one of the groups, if we do it with a more formal approach, the fall is not going to be an outlier, the winter is going to be an outlier, and then the spring and the summer. So we're still going to fall into this situation where I have something like this, where 3 of them are suggesting that I'm not an outlier, but one of the categories is suggesting that I am. Now, in class, we talked about some of the failures that we have in this approach that we are taking. So let me talk about a third failure that we're going to be confronted with. And that is the idea of an family-wise error rate. So if I go about doing my decision-making in a repeated manner, So a p-value of 0.14, that was for fall. That is not less than 0.05, so it's not statistically significant. But if I use 0.05 on every single season, my family-wise error rate could be as high as 20% because I'm using 0.05 on all 4 categories. Okay, so we certainly don't want to be making a decision with up to 20% error. Now, this is a maximum error rate. We do have a more exact formula here for that family-wise error rate, and that's given by this quantity right here, where K is just the number of tests that you're going to be running. So I have a little table here. If I run 4 tests, so I had 4 categories here. If I do 4 individual tests, my family-wise error rate using this formula right here is going to be 0.19. If we just cheat and use the shortcut formula, the maximum error rate is what I said a moment ago, which is about 20%. So again, we don't want to be making a decision with up to 20% error. That is way too high. We want this to be at a 0.05 level. There is a shortcut idea. It turns out that it doesn't work very well, but that is called Bonferroni's approach. And what Bonferroni says is instead of using 0.05 on each of these, why don't you use 0.05 divided by 4? Because then my maximum error rate would be 5%, right? If I add all of these up across the 4 categories, my maximum error rate would be 0.05. So this little trick, or this idea that I'm just going to take my 0.05 and divide by the number of tests that I want to do, that's called Bonferroni's adjustment. Okay. It turns out, though, that this Bonferroni adjustment does not work very well in a wide range of problems. So that's not something that exists, but it's not something that we use very often. What's going to solve all of this, like we talked about at the end of class on Wednesday, is if I have one research question, I want to get down to just 1 p-value. I want to try to get away from the 4 p-value situation. That's going to help me certainly with my error rate problem that I'm talking about here, because if I only have 1 p-value, then I can just compare it against 0.05, and I don't have to worry about this family-wise error rate that we're talking about here. The other thing, the problem is we really have not figured out how to combine p-values. So if I do have 4 p-values here, is there a way that I can just easily combine the p-values? We don't have an answer to that. In 2023, we do not have an easy way to combine p-values from multiple tests. This whole idea here where I'm using several p-values is called a multiple testing problem. And the multiple testing problem, as I talked about, ends up with this issue of the family-wise error rates. So like we said in class, what we want to be able to do is try to get it down to just 1 p-value. 1 graph, 1 p-value, 1 decision, 1 research question is the mantra. So what are we going to do instead? So this is what Carl Pearson came up with for the chi-square test, is instead of trying to gauge the degree to which I'm an outlier in each graph, what we're going to do is just measure how far am I away from the expected. Okay, so I was at 32 for fall, right? So I'm just going to take 32 and figure out the distance between 32 and the expected. So whatever 32 minus 25.75, I think was the expected for this problem. So that math here is on the bottom of page 10 here. So if I just take 32 and subtract 25.75, I end up with a positive 6.25. Let's go ahead and try to do that distance calculation for winter now. So let's go to winter, and what I'm going to do there is take 17, okay, is where I'm at. So I'm going to take 17 minus 25.75, and I'll get that distance. And if I do this across all 4 of my categories, I can get a total distance. So that is going to be the way that we can attempt to try to combine the distance I am away from the expected across multiple categories. I have 4 categories here. So if we do that math for each of the categories, we started doing that here. So 32 minus 25.75, that gives me 6.25. 17 minus 2575 gives me a negative 875. I have 30 here, so if I want to keep track of this, 30 minus 25.75, that is going to be a positive, what is that, 4.25, I believe. And then here I have 24 minus 25.75, which is going to give me a, keep track of the negative sign, negative 1.75, I think it is. Okay, get all that lined up for you. Need an equal sign here, there we go. And now all I need to do is just add these up. So if I take the positives here, so let's take 6.25 and 4.25, that's going to add up to 10.5. And then I need to subtract, so let's go ahead and do this. I got 10.5, 10.5, and then I need to subtract 8.75. And then I need to subtract 1.75 for that category. So my total distance is going to be 0 here, it looks like. Let me try that math one more time. So if I have, let's see here, let's just do these individually. Certainly the two positives is 10.5, the two negatives, so the two negatives here, move this out of the way a minute. Two negatives are 8.75 plus 1.75. That's 10.5 as well. So what's happening here is my total distance, when I add all of that up, I get 0 here, which doesn't really make sense to me because I can see from my red lines that I definitely have some distance away from the expected. This problem is going to come up in lots of different situations when I try to do something like this. And what's happening is that the positive distances are just canceling out the negative distances. This is going to happen when we compute a standard deviation or a variance. Okay. This is something that we run into quite often in stats. So again, what's happening here is the positive distances are canceling out the negative distances here. So my total distance, when I just add them up, is going to be 0. What I need to be able to do is, well, to be honest, what I need to, this here is, what do we say, 6.25 away? And this here is 8.75 away. I don't really care about the negative part of it. It's just 8.75 away. So I don't really need to worry about the negative values here. I just need to look at these distances. Now there's two ways that we can get rid of negative values with math. And the first is to square the numbers. So if I take a negative number and square it, I end up with a positive. That will get rid of the negative problem if I squared all of these. The other thing that we could do is use the absolute values. So instead of doing, again, instead of worrying about the negative, just say, well, that's 8.75 away. So just literally remove the absolute values, would just literally remove the negative signs from these two quantities. And if that was, what, 10.5 and another 10.5, then I would be at 21 would be my total distance if I did the absolute value thing. And that's a legit way to do it. It turns out, though, that we actually use the squaring of the numbers instead of the absolute value of the numbers. So we're going to keep these negatives in here for now, and we're going to end up squaring them instead of taking the absolute value. And the reason we do that is really just because of the mathematics that's in the background of a lot of the procedures that we do, which is beyond the scope of the class here. But squaring, a squared function has better properties than using an absolute function. So that's what we do, is we actually square these distances. So that's what we're going to do in the next table here. So here are those distances: 6.25, negative 8.75, 4.25, negative 1.75. We're going to square each of those. So 30, this right here is just 6.25 squared. That's how I got that 39.06. This here is negative 8.75 squared. Okay, and that's where I'm getting that 76. I'm going to take 4.25 squared, I get 18. I take negative 1.75, I get 3.06. Now I'm going to sum all of those up and I get a total of about 137. So the total distance, granted it's a squared distance, but the total distance that I'm away from the expected, okay, I have condensed that down to a single number at 137. So let's go back up here. We're going to take these distances. We're going to square them. Now I need to do the squaring so the positives don't cancel out the negatives. So I take this red line, square it, take the distance in this red line, square it, square it, square it, add all that up. That is going to allow me to take my data, which is 32, 17, 30, and 24, and condense it down to a single number. And that single number here turns out to be 137. So now, like we said in class on Wednesday, I've taken my data and smashed it down to a single number. I need to figure out whether or not 137 is an outlier. Okay, well, against what? How do I build a reference distribution for this thing, for that 137? Well, we're going to do what we were doing before, and that is generate data under a situation of equality, assuming that the crimes were occurring equally. We're going to do the subtraction from the expected, 2575, and we're going to square those. And then we're going to add all those up. That's what I did with my data. That's what I have to do with these null values as well. The first time I do that, I get 257. So this 257 is a number that I got under a situation of the crimes occurring equally. Here's another one, 24, 20, 27, 32. I need to put each of these, just do the same math that I did with the data. So 24, 20, summer was 27, winter 32. Subtract off the 2575, hidden there behind that, hidden there behind the parentheses there. But take 24 minus 2575, square that, get a number. Take 20 minus 2575, square that, get a number, and add all that up. You'll end up with 77. So there's two of the numbers that I could have gotten under a null model, or under a situation that the crimes were occurring equally throughout the year. So I would just plot out 257. I would plot out 77 all the way through. I'd end up with a whole bunch of those. So I just did two here, but you could do a whole bunch of them. This is the graph that we end up getting when I plot out a whole bunch of these collapsed data values. Okay, these are just data values, air quotes around that maybe, because these are the actual data values, but I need to condense that information down to a single number. And we do that by subtracting off the expected for each category, squaring it, and then adding all those up. Now, some things that are going to happen here is I'm going to end up with a lot of dots on this low end. That is because I would anticipate a lot of these counts to be pretty close to the expected, right? These counts here should be pretty close to the expected. So when you take a small 24 minus 25.75, that's like 1.75 or whatever, and then I square that, that's going to stay a pretty small number. And then when I add up four pretty small numbers, I'm going to end up with a pretty small number. So on these reference distributions and this approach that I'm doing here, I'm going to have a whole bunch of dots on the left side. These are actually going to be skewed distributions. So if you look up what a chi-square distribution looks like, they're all pictures of them are skewed. They're skewed off to the right. They'll tail off to the right here. The other thing that I do when I do my p-value calculation is just look at dots that are as extreme or more extreme than 137. Now, these are always right-tailed probabilities on this chi-square distribution. That is because what we do here is we square. So let's go back to my picture here. This distance right here is a long ways down, right? It's 8.75 or whatever away. But in that, my process of collapsing the data, I took that negative 8.75 and I squared it. Okay, well that, if I take negative 8.75, that's going to make it a very large number. Right? The lower side on this is 0. Okay? 0 means you're very, very close to the expected across all the categories. Values up here mean you're far away from the expected. On both the left side, because I'm squaring, and the right side. So again, outliers on the left side of those reference distributions up above, I take that information and then I square it, which makes it a large positive number. So everything, all the chi-square p-values from chi-square distributions are always calculated up on the high side, on the right side. For this analysis that we're talking about here, all p-values are right-tailed because of that squaring that's happening. In the context of this particular example, we have a p-value of 0.16. I have one p-value now. That is not less than 0.05. Okay, so does this p-value provide enough evidence for the research question? No, it does not. Okay, the reason being is that my p-value is not less than 0.05. So we do not have enough evidence for this research question. So my final decision here, the final decision here is we do not have enough evidence for a research question. Obviously, we'd want to write out a more careful conclusion than that. I don't know why we'd want to write that out a little bit more carefully, but you get the idea here. Okay, what we're going to do next then, and get that onto the next page, is look at situations where the proportions are not all equal. Okay, so what we did above was 25%, 25%, 25%, 25%, and that made my life a little bit easier when it come to looking at these distributions. But now we're going to let these distributions, these reference distributions, start moving around. We're still going to apply the same idea where I look at these distances and square those distances. But we'll do that on, I guess, Monday. So thank you all for listening. Have a good weekend, and we'll see you Monday in class.